Imagine a patient whose cancer responds exactly as expected. After treatment, the tumor shrinks, the scan looks clean, and the therapy ends. Months later, the cancer returns resistant to the same drug. This is a typical pattern in oncology, but what if I told you this is mathematics and not in the sense of probabilities, but in the structure of the process itself? To visualize it, we need to stop thinking about cancer as broken cells and start thinking about it as a mathematical search problem. In evolutionary biology, there is a formal concept called a fitness landscape. A fitness landscape describes all possible biological states and how well each one survives in a given environment. For cancer cells, that landscape is enormous. Most possible states are lethal to the cancer cell. Only a small fraction allows cells to survive. Cancer progression can be understood as movement on this landscape. As cancer cells divide, mutations occur. These mutations are random. They don't aim towards survival or improvement or resistance. If a particular mutation happens to work slightly better in the current environment, those cells divide more often, so that version of the cancer becomes more common. Over time, the environment determines which state persists and which disappear, and together this process forms a blind search through the landscape, with no foresight or goal. Before treatment, the fitness landscape has a clear ordering. Resistance typically comes with a cost. In the absence of therapy, resistant states occupy lower regions of the landscape, where they divide more slowly and are outcompeted by cells on the dominant peak. And treatment redefines which landscape regions are viable. The drug collapses the dominant peak into a lethal region, removing it entirely from the space of admissible states. The region associated with resistance, previously a valley, remains largely intact. Once the dominant peak is eliminated, relative height, how fast the cell population grows, or whether it can grow at all, loses its original meaning. What was once mediocre now defines the upper boundary of survival. The population didn't improve, but resistance still emerges because the geometry that determined success was inverted. And from the perspective of the search, nothing unusual happened here. The same random steps continue and the same selection rules applied. What changed was not the process itself, but the constraints defining which states were viable. This is why resistance doesn't require foresight, learning, or cancer cells trying to survive. Resistance is a predictable outcome of adaptive search in a landscape whose constraints are externally altered. This mathematical model might not really explain everything about cancer, but it does clarify an important distinction. Eliminating most cancer cells is not the same as controlling evolutionary dynamics. And when interventions reshape constraints without accounting for the landscape structure, they can preserve pathways to relapse. This geometry shows that managing cancer is about really controlling the landscape shape rather than just clearing its highest peak. Well, who would have guessed mathematics and medicine can be so groundbreaking together, right?